Okay, so let us continue. So can you finish the job? So was it clear what we did? So we want to look for a delta so that this works. What I did, you gave me an epsilon. I gave that epsilon to this part of the assumption. I get a capital N. I get this capital N and by the way, I get a capital N with this property. So two particular cases of this implication are written in green here. So hopefully you are convinced with these two. And now the assumption that I haven't used so far is this assumption that these functions are also continuous. So if they are continuous, all of them are continuous. The one with index capital N will also be continuous. And it means that it is continuous at P. So now I can have a delta with this property. I have divided the still epsilon by 3. Now my claim is that this delta that I am looking for is the delta that I got it here. So claim, the claim is that let x be in D and absolute value of x minus p be less than delta. Delta is exactly delta here. We show that what? Can you complete it for me to see that if you are following me or not? This is the claim. We show that the claim let so it is not a good way to write the claim in this way. Then and you complete it for me now, what should I write here? You are pointing to the correct one.
Yes.
F of x minus f of p is less than epsilon. Yes, this is what we want to prove. Okay, so let us start doing this. The trick is using the triangle inequality 3 times. So it means that I can write it as f of x. I mean, one expanded version of the triangle inequality. So I want to write this in this form. But I have to be careful to what are the things are involved. I want to write it as fnx plus fnx minus fnp plus fnp yes, and then what's more? Fnx I have, and then I want to have this one and that one and minus f of. First of all, do you agree what I have written is correct? Because this is gone, and I am left with that. Yes? But now, if you don't mind, let me put them in pairs. Yes? And I want to use triangle inequality. So this becomes less than or equal absolute value of the first one plus absolute value of the second one plus absolute value of the third one. Do you agree? Yes? But now let us see. This one, of course, it doesn't matter if I interchange them because that's absolute value. What do I know about the other way around of this? Because x minus p is less than delta, this is guaranteed to be less than, oh, that is not that one. Which one?
A little.
Here. This is number 2, yes? So this is number 2. This is number 2. This is less than epsilon over 3.
That is number 1.
What?
That is number 1.
No, that's number 1. Yes. Where is number 2?
To the right.
This one is number 2. Yes, so this is number 2. That is also less than epsilon over 3. But what about the middle one? The middle one is this one. Why this works? because x minus p is assumed to be less than that delta. So this one is also less than epsilon, and that is your epsilon. Okay. So it was a little bit tricky, but it's understandable. It's not hard. Okay. Any questions? So remember that from now on, uniform continuity will keep uniform convergence keeps continuity intact. Okay, so the next theorem, I don't want to go through the proof. If we have time, I will come back to it, but I just want you to know about the theorem so that we can finish this part. My main goal is to go back to the integral ones that we left, and then we complete everything today. So this theorem, it is also telling you, see, after continuity, I jump to Riemann integrability. I didn't talk about differentiability because that's a little bit subtle. I have written it in the notes, optional. If you want, you can study that. So it turns out that for differentiability, even uniform convergence is not good enough. We have to add a little bit more assumption on top of that, so to preserve differentiability. But for Riemann integrability, it turns out uniform convergence is also good enough. So let us go to the topic, and if we have time, we come back to prove it. Otherwise, you can read it from the notes. And today I was reading my proof. I realized that my proof was not the best one, so I will rewrite it and upload it, okay? Because it is correct, but I have jumped some steps like the books, you know. I have to explain things for you. I will do it for you and upload it. Okay, so let us read this one. So theorem 14.12. So what do we have again? Here, because I'm talking about Riemann integrability, the theory of integrability of Riemann integrals is only for bounded functions, okay? So here, when I say that I have a sequence of functions that are Riemann integrable, I am also sending you the message that these are bounded functions, okay? So this means that all of them are Riemann integrable on the intervals from A to B. And then we know that these functions are uniformly converging to a function f. So what type of function is this? I don't know if it is bounded or not, but I know that this function is also a function on the same domain. Okay? So the claim is this. The claim is that this one is Riemann integrable. So if I have a sequence of Riemann integrable functions, and if they uniformly converge to a function, that function is also Riemann integrable. Okay, number two, we have something more for the formula. So if this sequence of functions are Riemann integrable, what does it mean? It means that I am allowed to write this for all of them, and each one of them becomes a number. That's the meaning of this function being Riemann integrable. So this means this function, this integral for every one of these functions exists and is a number. So if I ask you, what do I have now? I have a sequence of numbers. So then I can ask, do you think that this sequence converges or not? Okay? The answer is yes, it converges, and also we know the value. The value is the integral of the converging function. So this theorem has two parts. The first part is that f is Riemann integrable, and the second thing is that the limit of these functions is this one. Is that clear? What is the content? Yes? I don't want to prove it, as I told you, but let me just give you ask you one, what do you think about? If I want to prove this, what is the first thing I have to prove and show it to you? Because I know my functions are all Riemann integrable, so it means that all these functions are bounded. Otherwise, I cannot even talk about Riemann integrability, because we only talked about Riemann integrability of bounded functions. But now my claim is that f belongs to here. Of course, I have to prove much more, but one thing I have to convince you about is that this function remains bounded. Because if it does not remain bounded, it doesn't make even sense to talk about Riemann integrability of that one. So let us just, to do something, let us just prove this boundedness, okay? One, we first prove that f is bounded. Okay? So how do you think we can show that? Because Fn converges to F uniformly on A and B, from this one, do you agree that I can conclude that there is an n such that for all x in A and B, if n is greater than or equal to n, then absolute value of fn of x minus f of x is less than 1. Do you agree? So I am choosing epsilon to be 1. You are telling me that this converges to f uniformly. It means for every epsilon I can find a natural number with that property, and I have chosen epsilon to be 1. Okay? So it means that this is valid. Okay, by why this is good, hopefully you know why. So it doesn't matter which number you choose actually here. You will see why. Because I want to use boundedness of these functions to conclude the boundedness of my function. So how can I do that? So I would say that now let x belongs to A and B. Okay? So do you agree that absolute value of f of x is equal to absolute value of f of x minus f capital N of x, this capital N is this capital N, plus f capital N of x. Do you agree? Okay, and then what happens, this is less than or equal to the absolute value of the first one plus absolute value of the second one. But in the absolute value of the first one, I interchange it because it doesn't matter. Yes? Okay, but this one is definitely less than 1. Because this is working for all indices greater than or equal to n, this index is n. So that's correct. This one is less than 1. Yes? So this one is less than 1. But what about this one? So I would write it as less than 1. But how? Just one line you finish the proof. Because I want to show that this is bounded. So I have to show that the absolute value of f of x is less than a fixed number. It is not a fixed number yet, because it depends on x. But do you agree that this is 1 also plus m? If what is m here? Because all these functions are bounded. So it means f capital N is also bounded. So it means that the absolute value of all of them are less than a number. That number is the upper bound for fn. So this is just the bound for f sub n. Is that right? Okay. And then for the rest, you have to see the proof. I will probably to fix the proof a little bit so that it is easier to follow. Any questions? Okay, so let us see what we have now. Okay, this is finished. Sequences of functions are finished. Then we have only a series of functions. But how do you yourself define a series of functions and these topics? So here, what do we have? Do you remember? If I want to talk about 13 before that, let me just remind you, when I have a series of numbers, I have something like this, yes, K. Do you remember what was the definition of convergence or divergence of an infinite series of numbers? From every series, you first set up a sequence, which was called the sequence of partial sums. So it means that you set up sequence Sn. How Sn is defined? Sn is defined to be the sum of the first n terms. So using this series, you set up a new sequence. So now you have a sequence. You don't have any series anymore. But then you investigate the convergence or divergence of this new sequence. If this sequence converges to S, you would go back and say that this series converges and its sum is that S. If this sequence diverges, you go back and say that this series is divergent. So that's the definition of convergence and divergence of series of numbers. But now, in this topic, I want to change these numbers with functions. Okay, so again, I have a sequence of functions, yes, and then I want to construct this series of functions. What is this guy at the end? If it is going to be something in mathematics, what do you expect this to be?
A number, right?
No, be careful. I am adding some functions. So if I have a function plus another function, what is this? I am talking about functions, real valued functions on real domains. So this makes sense. So what is the meaning of f? So f is a function, g is a function. When I add them, f plus g is also a function. But if I ask you what is the function, if it is a function, you need to tell me what is its domain. You need to tell me how it acts on its domain. So what is the domain? You have seen it in calculus. What's the domain of the sum? It is the same d. I cannot add two functions with distinct domains. The domain should be the same. And then for every x in that domain, f plus g acting on x means f acting on x, which is a real number, because the codomain is r, and then g of x plus. That's the meaning. So what I'm saying is that this symbol is no longer a number, it's a function. If it is going to be something, it's a function. Okay? What do you expect for the domain? The domain of all ingredients, but you don't know if it is convergent or divergent. So you have a function. If you have a function, you can more or less do the same thing. So you can construct Sn. Sn becomes the sum of a finite number of functions, which is a new function. Okay? So this means that I have a sequence of functions. Then the sequence of functions can converge pointwise. I will go back and say that this converges pointwise. Or the new sequence of functions can converge uniformly. If it is the case, I go back and say that this sequence also converges uniformly. Okay? So it means that this is a very simple task. We just translate it to the partial sums, the sequence of partial sums, and then we do everything we did before for this new. Is that right? For example, okay, I describe both of them simultaneously. So let us read this remark. The important point is that a series of functions is reduced to a sequence of functions by using partial sums. Thus, all the ideas we have studied for sequences of functions can now be applied to the sequence f sub n. Yes? For example, uniform convergence of the series means uniform convergence of the sequence of partial sums. Okay? For example, let us do this one. Example, this is 14.16. Let f sub k we have this, and then f sub k x is x divided by 2 to power k. Show that this series sigma k goes from 1 to infinity f sub k, converges uniformly on 0 and 1. So how should I do that? By the way, for this one, we have a very simple rule, and that is called Weierstrass M-test. We will learn it soon without proofs, because I want to go to that one. So, but let us test this idea just by definition. I want to show that this converges uniformly on 0 and 1. What should I do? So the first thing you do, you have to have this sequence. Okay, so let us have that sequence. So what is that sequence? It is just the sum of these functions. Be careful. So f1 up to fn. I want to prove, according to the problem, that this new sequence converges uniformly on 0 and 1. Do you remember, if you want to prove uniform convergence, you need to know you need to have some idea about the limit function. And I told you that the good candidate is to look at pointwise to find your candidate and then try to prove that that candidate also works for uniform continuity. So this means that I would say let x be a number here. Okay. This is because I want to investigate what is the limit function. Okay. So I would calculate this for that x. Okay. What happens? This becomes f1 of x plus fn of x. So what is this one? f1 of x is x over 2. f2 of x is x over 2 to power 2. And then finally I have x divided by 2 to power n. But again, be careful. This is uniform convergence. But in order to understand uniform convergence better, we need to do pointwise convergence to find the candidate and then prove that candidate also works for uniform convergence. This is why I have picked an x. Okay? Because in uniform convergence, it should be independent of x. Okay, but can you tell me do you think that this is converging somewhere for a fixed x there? For 0, it is trivial. It is 0. Okay, what is it converging to? This is a famous sequence. X is fixed, remember. So for example, let me factor x over 2, might be easier for you. Then it becomes 1. The next one is 1 over 2. The next one is 1 over 2 to power 2, up to 1 over 2 to power n minus 1. This is a geometric sum. So if I calculate this, it becomes x over 2 multiplied by the formula. This is not a series. Be careful. There are n terms there. So it becomes the first term, 1 minus 1 over 2 to power n, the number of terms, and 1 minus 1 over 2, the common ratio. This 1/2 and this 2 are gone. Okay, so it becomes x 1 minus 1 over 2 to power. Okay, but now my question for you is that, do you think it converges to something if I send n to infinity for that fixed x? Yes, because this goes to 0, this is 1, so it goes to x. Do you agree? Okay, but this is at the level of pointwise convergence. Okay, for pointwise convergence, Sn converges to x for every x. So can you guess what is the limit function?
X.
The identity function, yes? So we guess that for uniform convergence, the limit function is what? Is S from where to where? The same domain to R, to 1, to R, and then S of x is equal to x, not identity on this domain. This is your case. Okay, now you want to prove it. Okay, so what you should prove, I would say that so you see, this way was investigation to find my candidate. Okay, now I want to prove that this candidate is the one that takes me, the uniform convergence also converges to this one. I have to show that if epsilon is given, we prove that there exists an n in N such that for all x in 0 and 1, if n is greater than or equal to n, then absolute value of Snx minus Sx is less than that epsilon. Yes? But now you see why this was important to have this guess, because if I didn't have that guess, I didn't know what to put there. Okay? So now that I know what to put there, I just start from here. So Snx minus Sx is what? Snx, what was that? Snx, I calculated that, it is here, yes? Snx is this one, so that is mean that was not a waste of time. Minus Sx is just guess, okay? And what I do, I multiply this in, x's are gone, absolute value makes it this one. Yes? But be careful, I have to get rid of x because I want uniform convergence. Can I get rid of x? Because I want to make it less than epsilon. X is problematic. I have to get rid of x, but that's also easy because the maximum value of x is 1. So this is definitely less than or equal to 1 over 2. And of course, I can make it less than epsilon by choosing n appropriately big. So for example, what can I say? I can say that if I replace it, 2 to power n is greater than 1 over epsilon. So n is greater than, I don't know, ln of 1 over epsilon or something like that. And I would say that n should be great, is the natural number greater than that number. Yes? Is that clear? Okay. So this is done. But I just want you to understand this gymnastic. But for the exam, you don't need that because immediately we will have another theorem that is called Weierstrass test. So you can just do it using that one. Okay? And if you don't mind, let me just rush a little bit because I want to cover that part as well. So this one I skip because the reason I brought this is because I wanted to prove the Weierstrass theorem for you. But now that I want to skip the proof for that, there is no point to prove this one as well. All of them are written in the notes, so you can read them. But this one I want you to understand, okay? So if there is a question of sequence of series coming in the test, probably it will use this one, okay? So Weierstrass M-test, let D, so let me explain it here on the board for you so that we can go a little bit faster. So theorem 1418. So Weierstrass M-test. So what does it tell us? It tells you that if you have a sequence of functions, exactly as before, but I have changed the index from n to k now. K belongs to n. Okay, and then I can construct a sequence of positive numbers such that if I can have a sequence of numbers m sub k so that f, the absolute value of f sub kx is less than or equal to m sub k for every k in n. Yes, so you have a sequence of functions so that each one of them is bounded, but not bounded by the same number, bounded probably by different positive numbers. And if you are lucky and the sigma mk, k goes from 1 to infinity, converges, then the sequence f sub n, n goes, what I have written, k? Yes, sequence f sub k, k goes from 1 to infinity, converges uniformly. To what? God knows, yes? Converges uniformly. Weierstrass probably didn't care about that. Yeah? Finding the limit in analysis is usually hard. Convergence is good enough. Yes? Is that clear? So this is a very simple, by the way, the proof is also very simple. So I recommend you to read it yourself. But let us see that how it works. Can we go and solve that problem using Weierstrass test? So let us go backward and let us pretend that we are just solving that, but we know this theorem. Okay, so what was the function? What was the sequence? It was f sub k, and what was that the function fk? F sub k x was x over 2 to the power k. So what I want to do, I want to find an upper bound for these functions so that for each k. Okay, so it means that I would say let k be a fixed natural number. The absolute value of f of k of x is equal to absolute value of x, this one, but you agree that this becomes absolute value of x, this one. But do you agree this one is less than this one? Because I am working in this domain. So now, this is a fixed number. Why? Because it doesn't depend on x. So this is going to play the role of your m sub k. And now, look at the sequence. Forget about series, forget about functions. Just ask yourself, do you think that this sequence... sorry, what did I write? Ah, yes, sorry. It was too easy. Life is not that simple, you know. So this one, I have to check this one. If this converges, then I go back and say that this is sigma fk, k goes from 1 to infinity, also converges uniformly. But this is a famous series. Do you think it converges?
Yeah, converges to 1.
Yeah, because r is 1/2. So if r is a bit less than 1, it converges. So it's a geometric series, r is 1/2, absolute value is less than 1, converges. Then it means I go back and say that, okay, this series also converges uniformly. Okay, so for example, let me give you a little bit non-trivial example. So show that the series converges uniformly on this closed interval. Do you see why this works? And now it is very simple now by using this theorem. So 1419. Okay, so sigma x to the power of 2 cosine kx divided by k to the power of 3, and then I have k goes from 1 to infinity. We want to show that this converges uniformly on -2 and 2. Okay, if this is given in the exam, instead of doing it using definition, try to remember about the M-test. So the first thing you do is what? These are the sum of functions. So these are your functions. This is fkx. Okay, so let us look at the absolute value. And if you can convince yourself that all of them are less than a number, that number can depend on k, but it cannot depend on x. That is important. So this becomes absolute value. So how do you think we will do? We want to get rid of x's somehow. So the first thing I can write is this one. Do you agree? Yes, because the absolute value of cosine is maximally 1. So this is definitely less than that. I don't need absolute value because, oh yeah, I need absolute value. No, this is the power of 2 and k is a natural number. Okay, but still this is not good because x is there. So how should I get rid of x?
Swap it with 2.
Is less than
4.
4. Yes, because 2. X is
I mean swap
increase.
x with 2. 2 to the power of 2.
Yes, that's correct. So this means that instead of looking here, I just look at a new sequence. A new series. What is that series? So sigma, this is going to play the role of your m sub k. So sigma, k goes from 1 to infinity of m sub k, now becomes what? Sigma, k goes from 1 to infinity, 4 over k to power 3. Okay? But I have to convince myself that this is convergent. And I have written some of the calculus ones very shortly. Is this convergent?
Yeah, it's also geometric sum.
It's not a geometric sum. It's a P series.
Sorry.
Yes, harmonic series. So this is I can factor 4. This is 1 over 1 to power 3, 1 over 2 to power 3, 1 over 3 to power 3. This is not a geometric sum.
That is true.
But we have this one, yes, sigma. This is a very famous one. What is a P series? This is a P series. This is convergent if and only if P is greater than 1, and divergent if and only if P is less than or equal to 1. So because this one is greater than 1, that's convergent. And that is enough to write. You don't need to prove anything. So you say that this is a P series in which P is 3, and because P is greater than 1, this series converges. So this means by Weierstrass M-test, this series also converges uniformly. Is that right? Okay, so if you don't mind, let us just, this is finished. Let us go back a little bit. We have a little bit of time. At least I can point it out which parts are important. So this is very simple, but I just want to make sure that you remember them. So the definition of a primitive function, yes? So what was a primitive function? If I have a little f, capital F, whose derivative is little f, is called a primitive function for little f. And of course, you immediately, for example, let me show you the example. Consider these 3 functions that I have listed here. Can you see them? I have intentionally wrote them in a way that they seems quite different. Okay? And this is very simple exercise in calculus to convince yourself that all these capital F's are primitive functions for this one single little f by taking the derivative. If you take the derivative of f1, it becomes sine 2x. If you take the derivative of this one, 2 goes down, and this is the formula for sine 2x again. And if you take the derivative of this one, 2 goes down, and then you multiply by the derivative of the base, it is also the formula for sine 2x. And then you see that the derivative of all these capital F's is equal to f. But this hopefully looked like a contradiction, because yesterday we had a theorem that if the derivatives are equal, yes, on an interval, they should differ at most by a constant. Do they differ by a constant? Yes. Do you agree? Because sine x squared and cosine x squared, the sum is 1. So these 2 functions are really different by a constant. They differ by a constant. So it's not a contradiction, okay? So don't worry about the contradiction. So this is the theorem. Why this is true? If I have 2, let me just make it a little bit clearer. So if I have 2 primitive functions for the same function, they differ at most by an additive constant. Why? Because if both of them are the same, then it means f prime is equal to g prime. Then it means that f prime minus g prime is equal to 0. So this means f minus g totally prime is 0. But because the derivative of a function is 0, this was what we learned yesterday, f minus g is a constant. So they have to differ by a constant. Okay? This is an important theorem. This is the mean value theorem for integrals. We learned about mean value theorems for derivatives yesterday. Okay, so let me do this a little bit properly here. So what does it mean? It means that if f is a function but continuous, okay, and this means that this integral from a to b is equal to f of c times b minus a, where c is a number in the closed interval from a to b. Okay, so this is a very important theorem in integrals. So it means that if I have a continuous function defined on a closed interval, the integral, this is guaranteed that this integral exists because we learned that continuity guarantees integrability. So this integral exists and it has a value. This theorem claims that the value of this integral, no matter how complicated this function is, has a very simple form. It is the difference between b and a multiplied by f at one single point, which point again we don't know, but one single point in this interval. Because if we just knew that one, it was super simple. We could calculate all integrals if we know how to find that c. But the existence of this c, I want you to see the proof a little bit, because if f is continuous, because this one is compact, it means f of x is bounded. So this means that f of a and b is, let us use max-min theorem, okay? F is continuous, this one is closed. What you learned in calculus tells you that f of x is between two thresholds, yes? Between these two. And it attains the maximum and minimum. Capital M is the maximum of this function, little m is the minimum of this function, and they are attained in the closed interval. So now what happens is that we also learn something, that if this is the case, the integral of that should be less than or equal to the integral of this, should be less than or equal to the integral of that. But these are constants. We already calculated the integral of constant. It is just simply m times b minus a, less than or equal to the integral from a to b f, less than the same story for capital. Okay, and now I divide everything by b minus a, which is a positive number, so m is less than or equal to the integral from a to b f divided by b minus a, less than or equal to f. This is a number, a real number. Why? Because b minus a is a real number. This is continuous, so integrable, so that's a real number. So it's a real number. I have a real number between the minimum and maximum of a continuous function. So what can I conclude? According to intermediate value property of continuous functions, there exists a number c so that f of c is equal to this number. Because if I have a continuous function, and a value is between its minimum and maximum, that value is achieved. That is the intermediate value theorem. Yes? So this means that there exists so that f of c is equal to the integral of a to b divided by that. And if you multiply that, you get that result. And by the way, I have written it exactly in that way here. So that's the proof. You see, the proof was extremely simple. Okay? Now, the next one is the famous fundamental theorem of calculus. It tells you how to differentiate an integral. Yes? So let me just explain it here. We have to do a little bit messy work here. So, if you have, first of all, do you see that if I write integral from a to b, f is defined from the closed interval a and b to r, and it is continuous. That's important. Okay? So, do you see that if I choose x in a and b, do you think that this makes sense? And if it makes sense, what is this at the end? Is it a number or what? It's a number, but this number depends on this variable x. Yes? So if a number depends on x, it's a function of x. Okay? So that function of x, we call it capital F of x. And then the first fundamental theorem tells you that if you take the derivative of this function, it becomes simply this function. So let us take this x is out. So if you have a function defined in this form, the derivative of this function is equal to that function. Okay? So for example, if I ask you, I don't know, integral from 0 to x, and I give you e to power minus t dt, and this is a function of x. For example, if I ask you what is the derivative of this function, what's the answer? It's just this function. So it is e to power minus x squared. So it means that this function is a primitive function for e to power minus x squared. No one knows, by the way, no one will give you this in the calculus course, because e to the power of minus x squared does not have any primitive functions among the functions we know. But is there any primitive function for this function? Yes, this artifacted function. You might not like it, but that's a function. And the derivative of that function is this function. So this function is a primitive function for that one. But this function cannot be expressed in terms of logarithms or trigonometric functions, polynomials, the functions we know. But that's a function. Yes? Okay. So we have to stop here. I don't know how many, there are 3 pages left. And 2 pages are just calculus, so 1 page is more or less left. Okay, so I hope that, I wish you good luck, okay? So don't worry about the exam. In the meanwhile, if you think that is something emergency, you can write me an email. If there is a mathematics questions, I will not promise, but I will try to do my best to answer that. So if I couldn't answer, so no offense, okay? But I will try to do my best to answer. It depends how many emails I receive. Okay? And then please follow up what I wrote there. I hope that everything will be good. So, I mean, passing the exam is extremely, I would say, simple. I don't think it's a hard. But don't just study for passing, study for very high grades, okay? Okay, thank you very much and good luck. Thank you. Thank you. Thank you.